Hello everyone, welcome back to my channel, Mambalut's Math Tutorial. Today we will be discussing the graph of polynomial functions. The graph of a polynomial function is like a wave, just like what we have here in our picture, which is colored in orange. And it passes through the x and y intercepts of our plane, which are colored here in blue, which are the points A, B, C, and D. But how do we start to graph a polynomial function? First is we need the table of signs. This table of signs identifies the behavior of the graph, whether it is positioned below or above the x-axis. This is what the table of signs looks like. We have at the top the intervals, the next are the test values, and then in the left side we have there the factors and then the function, and then the position of the curve relative to the x-axis. Okay, let's have some examples. Example number 1. Graph f of x is equal to x times x minus 3. In here, our y-intercept is 0 and our x-intercepts are 0 and 3. So we will locate those points on our Cartesian plane. But our problem here is, where do our graph faces? Is it facing upward or facing downward? So to know the correct graph, we must now make the table of signs. But before making the table of signs, we must know first what are the intervals. And the intervals now are located between the x-intercepts. So we have the first interval, which are located on the numbers less than 0, which are colored there in blue. The second interval are the numbers between 0 and 3, which are colored there in orange. And the third interval are the numbers greater than 3, which are colored there in green. So from that intervals, we can now create our table of signs. There. So we have now the intervals. X is less than 0, which are colored in blue. Then x is greater than 0 but less than 3. And x is greater than 3. So from that interval, we will choose one value as our test value. So for x is less than 0, we have the value of -1. For x between 0 and 3, we can have the test value as 1. And for x is greater than 3, we can have 4. From these test values, we will substitute that values to the factors and identify the result whether it is positive or negative. So if -1 is substituted to x, the result is -1, so that becomes a negative. Then if 1 is substituted to x, so it is 1, is positive. And if it is x is equal to 4, so it is positive also. So for the second factor, which is x minus 3, so we substitute -1, so that becomes -1 minus 3, which makes -4. So the result is a negative. Then for +1, that becomes 1 minus 3, which is equal to -2. So the result is also negative. And if we have 4, 4 minus 3 is equal to 1, so the result is positive. And now for the sign of the whole function, we will multiply the resulting sign of the factors in each interval. So for the interval of x is less than 0, we have negative times negative, so that becomes now positive. And then for the interval of x is greater than 0 but less than 3, so we have positive times negative, which is equal to negative. And then for the last one, we have positive times positive, so that is a positive. So from there, we can now identify the position of the curve relative to the x-axis. If it is a positive, that means that the graph is located above the x-axis. And if it is a negative, it means that it is located below the x-axis. So we have there, for the x is less than 0, it must be above since it is a positive. Then the next one is a negative, so that must be below the x-axis. And the last interval is positive, so that would be above the x-axis. So from there, we can now graph our function by positioning its curve relative to the x-axis. So we have these intervals. So for x is less than 0, since it is above, so we can now plot it in our Cartesian plane as there, above the x-axis, colored in violet. Then for the second interval from 0 to 3, since it is below, so we can have our curve there below the x-axis. And for x is greater than 3, it is above. We have there above the x-axis. So therefore, the graph of our function is a parabola that opens upward. Example number 2. Graph f of x is equal to x plus 3 times x plus 1 times x minus 2. So from this function, y-intercept is equal to negative 6 and x-intercepts are negative 3, negative 1, and positive 2. So from that intercepts, we can have now our intervals there, which are colored in red, violet, orange, and green. So if we put it in our table of signs, we have the intervals x is less than negative 3, colored in red. Then x is greater than negative 3 but less than negative 1, colored in violet. Then x is greater than negative 1 but less than 2, colored in orange. And x is greater than 2, colored in green. Now let's have the test values. So we have negative 4 for less than negative 3. And then between negative 3 and negative 1, we can have negative 2. Then between negative 1 and 2, we can have 0. And for greater than 2, we can have 3. So we substitute now the test values to the different factors. So we have, okay, negative 4 substitute to x plus 3, so that becomes negative 4 plus 3 is equal to negative 1. So the result is negative. Then the negative 2 is substituted to x plus 3, so that is negative 2 plus 3. So the result is 1. So therefore, we have there a positive. Then 0, substitute to x plus 3, you have 0 plus 3, so that is 3, so positive also. And then if x is equal to 3, so 3 plus 3 is equal to 6, so therefore it is also a positive. So the next factor, which is x plus 1, we have negative 4 plus 1, so that is negative 3, so the result is negative. Then negative 2 plus 1, the result is negative 1, so we also have a negative. Then 0 plus 1, that is 1, so we have a positive. And then 3 plus 1 is equal to 4, so positive also. For the third factor, which is x minus 2, we have negative 4 minus 2, so that is negative 6, so the result is negative. And then negative 2 minus 2, that is negative 4, so the result is negative. And then for 0, 0 minus 2 is negative 2, so the result is also negative. And if we have 3, 3 minus 2 is equal to 1, so the result is positive. Now we will multiply the signs in each column to get the resulting sign of the whole function. So we have there, for the first interval, we have negative times negative times negative, so the result is a negative. For the next column, we have positive times negative will result to positive. Then for the next column, we have positive times negative, so the result is a negative. And for the last column, we have positive times positive, so the result is also positive. So we are now ready to get the position of the curve relative to the x-axis. So the first column is a negative, so that would be below the x-axis. Next is a positive, so that would be above. Then we have a negative, so that is below. And then the last one is positive, so that would be above the x-axis. So we are now ready to plot the graph of our function in our Cartesian plane. So points A, B, C, and D there are the intercepts of our function. So if we have the result of the table of signs, which is there, so if x is less than negative 3, that would be below. So if we plot that one, that would look like this one. So in green color, so that is below the x-axis for the numbers less than negative 3. And then if we have negative 3 to negative 1, that would be above the x-axis. So we will have the curve above the x-axis. They're colored in blue. And then the next interval is below the x-axis from negative 1 to positive 2. So we write there the next curve, which is below the x-axis, colored in violet. And observe that it passes to point D, which is our y-intercept. And then the last one, if x is greater than 2, it would be above the x-axis. So we put the curve above the x-axis there, colored in orange. So that would be the resulting graph of our function in example number 2. Now looking back at example number 1, the degree of our function is equal to 2 because we have two factors there. And if we multiply the factors x times x minus 3, the result would be x squared minus 3x. So the degree is equal to 2. And if we look at the graph, the number of turning points is just equal to 1. When we say turning point, it is a point where the graph changes its direction from falling to rising or from rising to falling. So in this case, in our graph, the turning point is located somewhere here. They're highlighted in green. In example number 2, the degree of our function is equal to 3 since we have there 3 factors. And if we count the number of turning points, we have there 1 above highlighted in green, and then below we have 2. So we have 2 turning points. Now, if we relate the number of turning points to the degree of the function, we can observe that it is just 1 less than the degree. So therefore, the number of turning points is equal to n minus 1. So whatever the degree of our function, we just subtract it by 1 to know the number of turning points of our graph. Now let's have the multiplicity of roots. This exists if we have identical roots. For example, if we have the function f of x is equal to x times x plus 4 squared times x minus 5 cubed, then y-intercept is equal to 0 and x-intercepts are 0, and then negative 4 multiplicity of 2, since the negative 4 root there has an exponent of 2 in our factors there highlighted in green, and 5 multiplicity of 3 since 5 has an exponent of 3. To graph this function, we need now the intervals. So the intervals there are x is less than negative 4, which was colored in orange. Then x is greater than negative 4 but less than 0, which is colored in blue. And then x is greater than 0 but less than 5, which is colored in green. And then x is greater than 5, which is colored in red. Then we can have now the test values, which are negative 5 for x is less than negative 4. And then for x between negative 4 and 0, we can have negative 1. Then for x between 0 and 5, we can have 1. And for x greater than 5, we can have 6. So we will now substitute these test values to our factors. So for the first factor, which is x, so we have a negative, since we have negative 5, substitute to x, so that is a negative. Then negative 1, substitute to x, so negative 1, so we have a negative. Then for 1, we have positive 1, so that would be positive. And then if 6 is substituted to x, so that would also be positive. Then for the second factor, which is x plus 4 is squared, we have positive all in all. Why? Because any number, positive or negative, raised to the power of 2 will always result to a positive value. And then the next factor, which is x minus 5 cubed, we have negative 5 minus 5 is negative 10. Then negative 10 cubed is negative 1000. So the result is negative. Then if we have negative 1, negative 1 minus 5 is equal to negative 6. And then negative 6 cubed is equal to negative 216. So the result is also a negative. Then if we have 1 for the next column, so 1 minus 5 is negative 4. And negative 4 cubed is negative 64. So the result is also a negative. And for x is equal to 6, so 6 minus 5 is equal to 1. Then 1 cubed is also 1, so the result is a positive. So we have now the different signs for the different factors. We are now ready to multiply these signs in every column to get the resulting sign of the whole function. So for the first interval, we have negative times negative. The result is positive. Then for the second interval, we have negative times negative. So it is also a positive. And then for the third one, we have positive times negative. So the result is negative. And for the last interval, we have positive times positive. So the result is also a positive. So the position of the curve relative to the x-axis are, for x is less than negative 4, it would be above the x-axis. Between negative 4 and 0, it is also above. And then between 0 and 5, it would be below. And for x is greater than 5, it is above on the x-axis. So if we plot that one on our Cartesian plane, we have now the x-intercepts. And now we will plot the curves in our Cartesian plane. So we have, for x is less than negative 4, it would be above to the x-axis. So we have there colored in orange. And then for the next interval between negative 4 and 0, it is also above on the x-axis. There, colored in blue. And then the next interval between 0 and 5, it would be below the x-axis. There, colored in green. And for the last interval with x is greater than 5, it is above the x-axis. So we have there colored in violet. Now, the degree of this function is equal to 6 because if we total the exponents there on our factors, that is equal to 6. So we must have 5 turning points. So let us count now the number of turning points of this graph. So we have 1, then 2, then 3, then we have here 4, and 5. So we have 5 turning points since our degree is 6. So 6 minus 1 is equal to 5. And observe also that if you observe at this point, our graph has a turning point on the x-intercept of negative 4 because negative 4 has a multiplicity of 2. So since it has a 2 degree for this root, so 2 minus 1 is equal to 1, so it must have a 1 turning point in this specific root. And for the root of positive 5, since it has a degree of 3, so 3 minus 1 is equal to 2, it must have now 2 turning points at this specific root. So that's why we have 2 turning points there. So totaling up to 5 turning points for the whole function. Now we have here the table of the behavior or the graph of the polynomial function, in which it could be a shortcut method in graphing our polynomial function without having the burden of constructing the table of signs. It is just by looking at the leading coefficient and the degree of the function. So we have 4 cases here, and for case 1, if the leading coefficient is positive and the degree is an odd number, so the behavior of the graph must be, on the left hand, it would be a falling, and for the right hand, it must be a rising. So example sketch of this is this one. So falling on the left hand and then rising on the right hand. And then, of course, you have to consider the number of turning points depending on its degree. Then the second case is, if the leading coefficient is negative and then the degree is odd, so the behavior of the graph would be rising and then falling. So the sample sketch is this one. So rising on the left hand and then falling on the right hand. Third case is, if the leading coefficient is a positive and the degree is even, so the behavior of the graph is rising, rising. So both rising on the left and the right hand. So this is now the sample sketch. There. And for the case number 4, if the leading coefficient is negative and the degree is even, then the behavior of the graph must be falling, falling. So this is the sample sketch. There. So falling on both sides. Now we can use this table to automatically approximate the graph of our polynomial function without having now the table of signs. So let's have an example. So going back to example number 1, observe that the leading coefficient there is positive and the degree is even since we have a degree of equal to 2. So that would be on case number 3. So the behavior must be rising, rising. So if we look at the graph, so it is a rising on both sides. In example 2, the leading coefficient there is also positive, but the degree is odd, since the degree here is 3. So that would be case number 1. So the behavior of the graph is falling and rising on the right hand. So therefore, the graph there is falling on the left and rising on the right hand. In example 3, the leading coefficient is positive and the degree is even because the degree there is 6. So it is also in the case number 3. So it must be rising, rising. So that is why the result of the graph there is both rising on the left and the right hand. Now let's have another example using now the table. So graph f of x is equal to negative x times x plus 4 times x plus 1 squared times x minus 2. So there, if we look at the leading coefficient, it is negative because we have a negative x there. And then for the degree here is 5. So therefore, the degree is odd. So that would be on the case number 2. So in case number 2, the behavior of the graph would be rising and falling. So if we plot that one on our Cartesian plane, the graph must look like this. Okay, so observe that it passes through the intercepts which are negative 4, they're highlighted in blue, then negative 2, and then 0, and then we have positive 2. So in the left hand of our graph, it is a rising, and then on the right hand, it is falling. So observe also that on this intercept, which is negative 2, it has a multiplicity of 2. That is why we create a 1 turning point there on our wave. So if we count now the number of turning points of our graph, so we have there 1, then 2, there on negative 2, and then 3, and then 4. So we have 4 turning points since our degree here is 5. Now it's your turn to answer your modules. I hope you learned something from our discussion today, but don't forget to like and subscribe. Thank you so much. At your service, Ma'am Balot.